lecture series of the Interact Northwest Europe project. My name is Marcelo Muller. I'm a project manager at Pontis Engineering and work in the development of manufacturing processes for composites. Before that, I worked with the Netherlands Aerospace Center, also in the development and research of manufacturing processes for composites. Today, I would like to talk to you about a different approach for successful use of composites in e-mobility. First, I would just briefly like to introduce Pontis. We're an engineering company. We're specialized in the manufacture of advanced composite products. Our main markets are the wind industry, renewables, mainly on blade manufacturing. We work in e-mobility. We work for large OEMs and small companies. And we also have a background in aerospace, which we do some work for. We're a one-stop shop for solutions in composite manufacturing. We can provide design and up to manufacturing support. We have our own in-house design capability. We can help you with developing a prototype, develop processes, qualify materials. We can help you start up your manufacturing, and we can help you in supporting your manufacturing and optimizing it. We work with big OEMs. We support the market leaders, but we also work with small startup companies. We're an independent company and we have a global network coverage. We have offices in China and the US, and our headquarters are situated in Amsterdam. Now to the subject of our lecture, composites in mobility, e-mobility in more detail. And we are looking at two composites that have been successfully applied into the passenger car market for load carrying structures, but also interior panels. But often that was at the high-end part of the market, with the more expensive cars, which could afford to have more expensive materials used for performance reasons. Recently, BMW has developed the i3, which was a more affordable car and which was produced in larger volumes, which also was quite successful in reducing the weight of a car. It took 30% of the weight compared to a similar vehicle, and was able to reduce quite a lot of CO2 reductions over the lifetime of the car. But a lot of lessons were learned from this development, so it's not finished there yet that we all know that everything can be applied. Lessons learned from the BMW i3 is that cost is still an issue. There's still a challenge in the industrialized process. A lot of compromises had to be made to implement composites in the car. There's still a lot of manufacturing waste involved. We used fabrics that, well, for cutting, left a lot of inefficient use of the material, which is quite expensive, so that could use some optimization. And also the material itself, BMW uses thermoset materials, which are usually hard to recycle. So these are questions that still need some more investigation or need to be answered. So there's still some room for development of composites in mobility, and we can look into that in more detail in this lecture. Well, why are composites usually used? Well, to enable a lightweight structure. If you look at in electric vehicles, the weight trend is a little bit different than we would expect. If you look at the larger, let's say, high-end models, the Tesla, Audi, Mercedes, they are quite heavy cars compared to their internal combustion engine counterparts. The Volkswagen ID.3 is 300 kilograms heavier than Volkswagen Golf 7. This obviously comes because of the battery. So why are these cars not optimized for weight yet? Well, at the moment, the industry is such that people are electrifying their cars. They want to have an alternative. They want to offer their customers a car, an electrical alternative, so that they are not basically left behind with the competition. So the focus is not that much in making things lighter, but it's making things electric. So there is still some room for improvement at a later stage, but it's not the main focus here. I would like to just continue a little bit on the lightweighting parts. So the first priority is electrification. Once that's done, people also are talking about autonomous driving as a priority. Well, this has quite a lot of implications. It's quite difficult also about regulations, even the legal aspects of it. So it's not seen yet as the highest priority. So slowly also moving to the area that we would like to do some lightweighting. Well, why would we like to have some lightweighting? Obviously, extend range to make up for the battery weight that you need for that range. But one other aspect that can be kept in mind is that since we are having a lot of difficulty sourcing materials, there's a scarcity of materials for batteries, it could also be that you need to have to lightweight for different reasons, because you can either not afford battery that's larger because of the cost of the materials, or just these materials are not available in sufficient quantities. So then you'll be forced to lightweight your car because you do not have the battery to have a bigger range for a heavier car. But the actual need, do we really need to have this lightweighting? Well, I would like to explore a number of things. The ranges that current cars have might be sufficient. Nissan has got some feedback from their cars and their owners, is that concluded that if you have a driving range of about 300 kilometers, people are not that much concerned about the actual range. The range anxiety diminishes. They actually have sufficient range to do what they have to do, go to work or do shopping, and still have some left to do something unexpected, pick up the kids that got sick from daycare, for example. So that's not too much of a concern once they know they have sufficient range. So yes, additional range would be nice. You don't have to stop when you go on holiday, but they might not want to pay premium to get that extra 400, 500, 600 kilometer range from one battery. Also, you compare it with your mobile phone, you can have your car charge overnight and have it ready in the morning for you to start. Your mobile phone also, manufacturers do not put that bigger batteries in your mobile phone because everybody charges overnight and can use it for the full day. Everything extra is nice, but they're not quite willing to pay for it, so they leave it as it is. But one major aspect I think is quite of importance for let's say, the justification of making a lighter structure is energy regeneration. Recovery of energy by braking electric cars. The energy you put into the car when accelerating is recovered when braking. Compare it to an internal combustion engine that is lost and you get it back. This is becoming quite efficient in such a way that you have about 90% recovery of the energy. There's a study that cites that a model Tesla X of about 2,000 kilograms has been tested with an added weight of 300 kilograms, and the energy consumption increase of that car was only 0.6%. Which is quite marginal if you consider the added weight, the weight that you add to it is about 14% of the car structure. So that shows that you don't have that much to gain if you have energy recovery in a car. And again, people might not want to pay premium for that extra little bit of range that they might get from this little extra energy that you have to put in. One final aspect is the regulations for rest. Professional drivers, are subject to rules for resting periods, so they need to stop and take an amount of hours of rest before they continue driving. And during that break, of course, their vehicle can be recharged, so it's not necessary to have a bigger battery to overcome the extended long ranges they do, because they have to stop anyway to recharge. So these reasons make it somehow a little bit less obvious that you would put a lot of effort into developing a lightweight structure. But still, these are not the major reasons. They are something that play a role, but if you look at why not more composites are used in cars after BMW i3, well, one of the conclusions is that composites are still difficult to mass produce in the very high volumes that is necessary for these passenger cars. Cycle times are still too high, there's still too much steps involved in manufacturing, and the material cost is still not low enough to be able to be competitive. Add to that some risk in implementing a newer technology and investment there that's necessary, means that companies are quite hesitant to just make the step to the very high volume, low end cars, which means that it's usually getting back with the lessons learned from for example, the BMW i3 of implementing in a more cost-effective way composites in the more high-end cars, such as BMW i7, which now has a hybrid roof structure, or the Audi A8, for example. Over here is just to highlight what's necessary to get more composites going in, let's say, the high-volume cars. Basically, if you compare it to steel and aluminium, carbon is quite expensive if you look at on the right side here. 32 kilograms per 32 euros per kilogram. Obviously, it can get quite a considerable weight savings compared to aluminium, 30% to 50%, but the premium is quite heavy, 5 times more material price, and also 6 times more of the lightweight cost per kilogram compared to aluminium. So aluminium already gives you a considerable weight saving at a much lower cost. So that's a competition that's always present with carbon and lightweight structures. So what is necessary to really enable a breakthrough in the high volumes is that we need a manufacturing breakthrough. That can be either by the prices for raw materials coming down, or just by, let's say, making a big step in the manufacturing process, bringing down the total costs. Basically, what needs to happen is that these costs have to come down by a factor of 3. So there's quite a challenge to be met here. And, well, that is, I think, would be a bigger step too far if you would just try to implement in the high volumes that are necessary for passenger cars. So what if the volumes are a little bit lower? Then you could develop the technologies that to suit the higher volumes at a lower pace. You can investigate their scalability and transferability into these high volumes, and after you have validated, you can scale it up to the right volumes. This means that you basically would like to have some development at a slower pace, but still have some business case. Well, keeping in mind lower volumes, I would like to discuss the next subject, which are the commercial vehicles, electric commercial vehicles in this case. Commercial vehicles. Commercial vehicles are trucks, city buses, vans, etc., that are used for transport of goods and persons for money. They can be used for long distance deliveries, but if you look at the electric vehicles, these are mostly used for last mile delivery into city centers to deliver packages to private homes or goods to companies like supermarkets or other smaller enterprises. A lot of things are happening there. If you look at it, there's light electric vehicles. This is the latest area of interest, in which very small micromobility, stand-up scooters, bikes are used to deliver people and goods into a city. A number of things are happening. There's a lot of change going on. Compared to passenger vehicles, which require really design and manufacturing excellence, and you can really not afford to miss a lot. There's still a lot of development in the e-vehicles in the commercial side, because, well, basically the modus to what's the best solution has not been clearly defined yet. So there's a lot of interest there to develop that solution. That also shows that there's seen as a market with large potential. If you look at initial public offerings where companies raise money for development of their products in 2021, there were 3 big initial public offerings, where Arrival, a company from the UK, raised 11.5 billion euros. Basco, a bus manufacturer in the Netherlands, raised 1.3 billion euros for the development of their lightweight bus. And Rivian in the US raised over 10 billion to develop a van backed by Amazon, for example, for last mile delivery. So there's a lot of potential in this market. At least investors see that. So there are quite a lot of interesting prospects for commercial vehicles. They are interesting because, contrary to the Tesla I just mentioned, that only had 0.6% of energy consumption with the extra weight, that doesn't much matter to drivers, and they're not willing to pay that much for it. But if you look at a commercial vehicle, like for example a 3.5-ton last mile delivery truck, which has a limit 3.5 ton, making that vehicle lighter, 200 kilograms lighter, means that you can bring 200 kilograms of payload more with you, which is basically 200 kilograms of paying load that allows you to have an increased efficiency of your vehicle. If you make a bus 1,000 kilograms lighter, that makes it more available, so also increases the efficiency of your vehicle. For commercial purposes, that translates directly into money, and money can be just quantified more easily than the perception of just having a longer range. So it's much easier to quantify and justify the investments. But still, there are some challenges that have to be overcome to be able to develop these vehicles. And this is what I would like to discuss in the next few slides, which is the volumes involved, the requirements that are involved for these vehicles, and also the processes and their industrialization level. If we look at the volume in the market size, especially the volumes, the initial volume for the commercial vehicles is significantly lower than the passenger car markets. Tens of thousands, hundreds of thousands are the usual there for commercial vehicles. The typical product volume is 1,000 to 10,000 parts. That requires a different level of investment, but also opens the way to carry out to develop new concepts. And just to get an idea of the challenges involved in that part, I just would like to look at a few other different examples where similar materials are used to composites, but different challenges exist. And these are similar to what you could encounter when developing a commercial vehicle in composites. I would like to discuss a blade from a wind turbine, a bus, and a battery cover. First, a wind turbine blade. The one you see on the image is one of the biggest commercially manufactured blades currently in production. It's 100 centimeters long. It's mainly made of other glass fiber with carbon spar caps to give it some more stiffness. It weighs 54,000 tons, of which 10,000 tons is the carbon, and that's produced about 1,000 a year, so let's say 3 a day. This obviously gives you some challenges on how to manufacture such a large single-piece composite part. You have to make choices on how to do that and how to make that efficiently. If you look at another structure, you would make other different choices. For a composite bus, that's carbon fiber structure in this case, of about 1,000 kilograms compared to the 50 tons of the blade. That means that you can choose different manufacturing technologies to make about 1,000 to 5,000 pieces a year, which is quite a different number, but still very respectable. If you look at battery covers, these are typically more high volume parts. Carbon fiber, 5 kilograms, so they're small, they're lightweight, reasonably small mass, and you can choose other processes that you would never dream of using for a wind turbine blade. So again, you have to play with these requirements and the challenges that are there to match them together and get a good product. Making these choices are part of your development and phase. So that volume, depending on the choices you make, also can be looked upon in the development phases of your product. Initially, you have a concept, you detail it out, engineer it, do your concept phase, and get the initial prototype working. And at a certain point, you would like to, let's say, commercialize it. Then you need to do a few steps. Initially, if you see in the image here, for the first year, you will build a number of prototypes, let's say about 5, to demonstrate the feasibility, to do some extra trials, to show it to potential investors. So they'll build about 5 up to 5 prototypes, mainly by hand. Once you validated your concept, you met your goals, you would like to scale it up, you would like to make in the second year perhaps 50 units to do some prototype testing, to do some further validation, also to do work towards certification. That involves also time and money. And all the time, investors are looking into it if you are still developing and delivering on your promise. So you need to make sure that they are happy too. And then you have to make another step into full production, which requires 5,000, 10,000 parts a year. And that also requires quite a considerable investment there. So that requires a lot of effort, not only from a technical point of view, but also from a financial point of view. If you are a big OEM manufacturer, BMW or Renault, then you should either have an infrastructure, perhaps even have an RTM setup that you use, or you at least have the backup and the funding, the deep pockets that are necessary to put something in production. If you're a startup, that's a completely different issue. So that's also a very challenging area. We've seen that even Tesla has been had a lot of trouble ramping up their production. Rivian and Arrival, which I mentioned in the IPOs, also are having trouble financing their ramp up, and that after these big IPOs that they raise a lot of money, they still need more. That's not uncommon if you're going to stepping into the automobile industry, but it is quite a part that a lot of companies could fail. So that's also quite challenging environment. If you look at the proposal to just scale down on the development to develop a technology and scale it up later to have basically a phased approach for high volumes, you really have to keep in mind scalability. That is also important because then you can afford to do this development. Yes. Looking at the second bullet point I mentioned, the different requirements, there are also quite some challenges to be met. Local manufacturing is one of them. If you want to sell buses, usually the local authority you're selling them to, a city or a country, will ask you to do something in return by having the vehicles manufactured in their area to support the local economy, basically. That means that you have to change your logistics. You cannot have one big factory in which you manufacture all your products efficiently. You will have to either transfer some of your manufacturing to another area, or at least build your vehicles in sets that can be assembled locally. So that does not help in getting an efficient manufacturing process, especially if you have the low volumes involved for commercial vehicles. Also, these smaller series require you to have a flexible and agile manufacturing process because there's a lot of variation in these designs, but also because of the short runs, you have to be able to switch over to new production quite quickly without having to invest a lot into new equipment or a setup. And not only should your process be able to cope with that, but also your entire organization be able to cope with that from just organizational, but also logistics point of view. And the third item here is sustainability. This is becoming quite more and more important, so I just want to one important demand from OEMs and their customers is demand for sustainability. Customers want to know what manufacturers are doing for the environment. They want a sustainable product. They want to have a recyclable product, but even better it would be if the product would be circular, so that the product is recycled to be used in the same way it was before, so that you don't need any more raw materials to be used for a new product. Solutions are being developed in that part. Often you hear composites are hard to recycle. Yes, thermosets are not the easiest materials to recycle because they're quite so durable, but the industry is addressing that. There's already for glass fiber quite a good way of recycling by cement kiln route, where basically your glass composite is used as a raw material for manufacturing cement, saving on energy that's used for compared to new cement. There are thermoplastics that can be recycled also into the raw material. I'll talk about that a little bit later. But also, there's just quite an interesting development that has been gaining much more interest lately. It's basically reversible thermostats, whereby some chemical modifications of, for example, epoxy, the material can be behave as a thermal set at the operating temperatures, that at raised temperatures there's a chemical change in the material that makes it processable like a thermoplastic, which is much more easy to process and recycle. And there are also other methods for recycling available and being developed at the different stages of readiness, of course. But one thing to keep in mind is that solutions are available, and the important thing to do is to, when you're designing a new product, to take that into account so that you have a path towards recyclability and have already built out in your product. Obviously, that's not always easy because you don't know the exact outcomes, but if you take into account at the design stage, it's much more easy to implement than you have to just find a solution afterwards. And the final challenge I mentioned was the semi-industrialized processes. You have to have a scalable, automated, transferable process that is flexible, because you have to adapt to the limited volume and local requirements. And for that, you are developing new processes. They are hopefully based on some industrial process, but you always will do some modifications to suit that new product you're making. So you will have to take into account that there will be some effort necessary to bring it to the desired industrial level. So that's also a challenge you have to keep in mind when developing that product. That makes it a little bit complicated, but again, like I mentioned, if you're looking at the small volumes, you can still experiment a little bit to optimize the process and make sure you have a product that is really fit for purpose. But I'd like to highlight just two examples on how these challenges were met and some aspects of those. The first one is Arrival. It's a UK-based company that has built a clean sheet delivery van. They also work on buses and trucks, but the main focus is on the delivery van. They use a metal space frame, composite body panels using thermoplastics, and they have made a clean sheet design also with a modular approach. So variations in the size of the vehicle are easy to implement. Using thermoplastics, they use a combination with metals. They use a pressing method. They call it a multiform pressing method, in which you just quickly can press the panels at a low cost and just attach it to the car. They make sure that they don't have already the first surface finish incorporated in the panel, so they don't have a paint shop. They do this using a microfactory approach. Basically, they use dedicated cells, small robot cells that can do all the operations, the assembly, and that these are quite flexible to be set up in existing factories or locations, so they can put these cells where the production needs to be, and they don't need to have all the transport involved, and also can meet local assembly requirements. They also have taken sustainability into the design, so they look into the materials they use and the material waste, the production footprint, what the effects of there, but also incorporated all types of recycling streams into their production. So they make sure they try to tick all the boxes that are necessary to have an efficient and, let's say, innovative concept. The second example I would like to discuss is Ebusco, a bus manufacturer from the Netherlands. They built a metal bus currently, but they also have developed a composite bus which uses a carbon space frame, which compared to the metal product achieved 32% weight reduction. They use mainly carbon for their structure, some glass fiber as well. And they used as a manufacturing process aerospace manufacturing processes, but not at the aerospace price. They have translated it into a more affordable, efficient way, and by making smart choices on how to implement that. The technologies they use is overbraiding, which is an automated manufacturing technology in combination with RTM infusion for their structural parts. But they also use pultrusions, which can be reasonably standard parts that are all manufactured in an automatic way. And by combining them, they can make an efficient structure with great reduction for their additional range. These two are different concepts that tackle the similar challenges. They especially Arrival looks at the recyclability that they're designing to from bottom up. They both need a scalable process. They both are ramping up production and need to be able to cope with that, and the process needs to accommodate that from basically day one. Also, to ensure scalability, automation is involved in both examples. Local footprint, especially at Arrival, that's quite a strong one, but the use of automated processes and standard profiles enables Impossible also to have a more flexible approach. And both processes are quite agile and flexible for manufacturing. So, how about a different approach? As Pontis, we also have looked into a concept to, let's say, address the main challenges, and to look into a concept demonstrator vehicle. You can see an artist's impression on the right here. So what did we want to achieve with that concept? Basically, we want to have hybrid manufacturing techniques and materials, because we do not want to constrain ourselves to one material, because that poses some restrictions. So we want to use the right material where necessary, so that could be thermoset, thermoplastic, or even metal, to make the right use for the structure. We favor quite strong liquid thermoplastic materials. I'll talk about the advantage a little bit later. We also want to use integrated pull-through profiles, again, also because of the automation and the modularity of those parts. Because also this modularity and simplification, well, simple parts, enable it to be there either to be produced and assembled locally or just assembled locally, but allows you some flexibility for manufacturing process development. And also, from bottom up, the components should be recyclable. The entire vehicle should be recyclable. Well, our approach to achieve that is that we want to use a hybrid manufacturing techniques. We do not want to just focus on one material, but we want to use the right material for the job. That could be thermosets, thermoplastics, or even metals, or a combination of that for that matter. We strongly favor the use of thermoplastic materials for reasons I'll explain a little bit later. Use of integrated protrude and braided profiles, because they can be quite easily manufactured automatically, is also something we envision. Because they also help us to produce and assemble locally. You can either build your sets, kits, and ship it off to be assembled locally, or even because they're quite simple processes, you could produce them on site or at least close to the site. And again, we take into account that the entire structure needs to be recyclable in some way and integrated already into the design. Well, for that, you want to combine the vehicle design and part production. You just match things. You have to really make the best composite design and use the best suitable material. And for that, you need interaction between design and the material solution and the application. So basically what we say, you need to design for manufacturing so that you don't have to, after you have designed, have a translation from the design into manufacturing, but you have already that built into the solution. As I promised, some more details on the liquid thermoplastics we envision. We think that's quite an interesting area that can solve a lot of problems. Liquid thermoplastics can be used for the infusion process. We can combine these inserts, prefab parts. The liquid thermoplastic we're referring to is brought to the market recently, is Ealing by Arkema. In the past, liquid thermoplastics were available, but their processing temperatures were quite high, over 150 degrees or more. That required quite some investment in tooling, for example, and also, it's a more energy-intensive process. So that was not an attractive option to develop components. But since these new resin was available on the market that can be just cured at low temperatures or even room temperature, costs can come considerably down to use thermoplastics, and then you can take advantage of the properties that make it an attractive part, which is recyclability. Arkema has built-in recyclability, basically that they can either use it to repurpose the material as pellets in injection molding, but they also have a route in which they can just basically reclaim the matrix material and use it for the manufacture of a virgin resin material, which is a better solution because that makes the entire component circular. And one final very interesting and attractive aspect of thermoplastics is that they can be welded instead of bonding. You do not need an adhesive that needs surface preparation and cure time to join a part. You can just use welding by heating the material and pressing it together to assemble a part, and that can considerably increase shorten assembly times to increase the efficiency of the assembly process. All in all, quite an attractive way of to consider to apply to your product. Summarizing, well, I cannot give you a single solution for all commercial vehicle concepts because they're quite different and have their different needs and challenges, but there are a lot of solutions available, so you really have to understand and choose the right one that's the proper one for your product. Whatever it is, the composite business will need to show that it's robust and competitive. It needs to be able to fulfill a need. You might need to do a phased approach, not just want to jump to full series production of high volume in one go, but you might either take a step back and do it in the lower volumes of commercial vehicles, but you also can also consider designing with possible implementation of composites in the future. But consider designing a metal part and then translating that at a later stage when you have ramped up your production into composite parts to achieve these weight reduction. If we want to implement composites in the high volume passenger car business, a technological breakthrough is necessary. Prices have to come down either by materials cost that comes down or let's say a leap in the manufacturing processes that are available to bring down cycle times. And that is still a challenge, still work to be done. If you're developing parts, think hybrid, not limit yourself to one single solution or material. And obviously, with all what you do, sustainability is key. We need to keep in mind that we have to have a sustainable circular solution to be able to keep developing ourselves and create a greener world. This concludes my lecture. I hope you found it interesting. If you'd like to discuss some aspects in more detail, feel free to contact me at any time at Pontis, and I'll be happy to take some time and look into your questions with you. Thank you.